So we've talked a lot about naming and formulas for ionic compounds, but let's talk about the other option, covalent or molecular compounds. So this would be a great time to get out your periodic table, which you really need pretty much every day in this unit. So let's think about a couple of things that are a review first. One is the periodic table trend of electronegativity. So electronegativity refers to how attractive an element is to electrons. And the smaller an atom is, the higher the Coulombic plus minus charge attraction and the higher its electronegativity, because the closer charges are together, the more attraction they feel. So in this case, the trend is going to increase as we go up and increase as we go across the table. So the element with the highest electronegativity here is fluorine. Fluorine is set as the top of the electronegativity scale by the gentleman who invented the electronegativity scale, Linus Pauling. So the electronegativity of fluorine is 4. It's the highest thing on the whole scale. Immediately next to that, oxygen and nitrogen, also extremely small, extremely high electronegativity elements. You can see the things that tend to be the most electronegative are going to be the nonmetals on the right as you're looking at it side of the periodic table. So we started with ionic compounds talking about binary compounds. So we'll start in the same place here. Remember, a binary compound is one with only 2 different elements. That does not mean 2 different atoms, it means 2 different elements. For example, sodium chloride, a binary compound because it contains only the element sodium and chlorine. But carbon disulfide here, CS2, is still a binary compound, even though it has 3 atoms in it, 1 carbon and 2 sulfur atoms, because it has 2 elements, carbon and sulfur. So the biggest thing we have to do is to distinguish between molecular compounds and ionic compounds, so we know which set of rules to use when we want to name. And the easiest way to do that is to look at the component elements. An ionic compound is going to be between a metal and a nonmetal. So potassium bromide is an ionic compound. Remember, this is because ionic compounds are made out of ions, charged particles. So we need something that will lose electrons, like a metal, like potassium, and something that will gain electrons and become negatively charged, like bromine. On the other hand, a molecular or covalent compound is going to be all non-metals. We have to think about why that might be. Well, all of the non-metals have very high electronegativity. They're very attractive to electrons. And those are all elements that would normally gain electrons. There's nothing there, if everything is made out of non-metals, to lose an electron and make an ion. So they kind of have to suck it up and share, because they need that extra electron to get to the low energy state, and they can't take it from something, so they're just going to share with each other. At least you get a share of 8 electrons. So some examples here: carbon monoxide, CO. Carbon is a nonmetal, oxygen is a nonmetal. Hydrogen bromide, HBr, hydrobromic acid. Hydrogen is a nonmetal, bromine is a nonmetal. Methane, CH4. Carbon and hydrogen are both non-metals. So the naming is kind of similar between ionic and molecular compounds. Fundamentally, there's still 2 words in the name. The first word is the first element in the formula. So very similar to what we did with ionic, but with molecular compounds, because there's sharing of electrons, not adding and subtracting of electrons, there can be more than one way for elements to combine. Like we saw CO, carbon monoxide, on the last slide. CO2, carbon dioxide, is what we're breathing out. It's the product of cellular metabolism. So we need to find a way to tell between those two. The way we do that is by using a numeric prefix, and we'll go over those in a minute. So for example, N2O, the first word there is dinitrogen. Di for two, obviously nitrogen for the element. The exception here is something that I've noticed already. We said carbon dioxide, CO2. If we were going to always use a prefix, we would say it would be monocarbon dioxide, but chemists are lazy, and so we don't tend to use prefixes that we don't have to use. So there is no mono prefix on the first element. The second element is the second word. The second element always has a prefix according to that subscript. And just like before, it ends in IDE. So N2O would be dinitrogen monoxide. Mono means one. So here are those prefixes. You do need to make sure you know them. 1 is mono, 2 is di, 3 is tri, like a triangle, 4 is tetra, like a tetrahedron. The other ones are similar to what you learned in geometry. A 5-sided object is a pentagon, 5 is penta, 6 is hecta, 8 is octo, 10 is deca. They're the same prefixes that you learned for polygons back in geometry class. Tri and tetra are probably the two that I see people get switched around the most. And just remember, tricycle, triangle, things that have 3 are tri. Tetra is 4. So if you're trying to remember which one is 3 and which one is 4, remember when you were little, you might have had a tricycle. It has 3 wheels. Tri is 3. That means tetra must be 4. So here is a chance to practice a couple of these, and I'll do the first one with you, and then I'll pause and let you try. So the first word here is going to be hydrogen with a prefix according to that 2. 2 is di, so this is going to be dihydrogen. The last one is going to be sulfide with a prefix according to 1 here, and 1 is mono. So this is dihydrogen monosulfide. Okay, I'm going to let you pause this and try to do the next ones, and then we'll check your work. Okay, well, let's look at the answers here. N2 would be dinitrogen. 5 is penta. So pentaoxide kind of sounds odd. So instead we simplify it a little bit and say it is pentoxide. NO, okay, well, N would, if it was in the second word, it would be mononitrogen, but we know there's no monos on the first element only. So this would be just nitrogen, but the mono always shows up on the second element. So monooxide, again, it's hard to say, so we just simplify it as monoxide. So this is nitrogen monoxide. Again, no prefix on a first element only, so the first word is just going to be phosphorus. 3 is tri, like a triangle, so that is phosphorus trihydride. Hydride, okay? Oxygen, no mono on the first element, so this is oxygen. 2 is di, so this is oxygen difluoride. And my last one here, if this is a gas, is hydrogen monobromide. If you see this in water, it's acting as an acid, and it has a different naming structure that we'll talk about coming up shortly. But if it doesn't tell you to name it as an acid, it's just hydrogen monobromide. Sometimes, often, actually a lot of the time, you'll hear this just called hydrogen bromide. As a gas, sometimes you hear this just called hydrogen sulfide. A lot of compounds that have been known for a long time have common names that are used over the systematic name when the systematic name is longer or more complicated. Like CH4 would be carbon tetrahydride, but really everybody just calls it methane. It's natural gas, it's been around for a long time. So when we think about covalent bonds, we need to think about what is different between a covalent bond and an ionic bond. An ionic bond, remember, is the attraction between a positive ion and a negative ion. They're attracted to each other, so they stay together. Covalent bonds are formed between non-metal atoms because they're so close in electronegativity that they can't just take an electron from one another. So it's kind of a, well, I need to get to a low energy state. It can't just take an electron and get to the low energy state. So, well, if I can't take it, I guess I'll at least share it. Covalent bonds are made when two atoms are going to share an electron pair. One electron from each atom contributes to that pair. And that will get it closer to the low energy octet state. Two atoms can share just one electron each and have one shared electron pair. Or you can have two atoms each sharing two electrons, which would give you two shared electron pairs, what we call a double bond. Or you can even get up to having three shared pairs of electrons, which is what we call a triple bond. I would not do more than that in any time in honors or AP chemistry. So here's our example. Two hydrogen atoms, each one only has one electron. And so hydrogens, when they get close together, they share their one electron with each other. Then they at least both have a share of two electrons, letting them have the same number of shared electrons as helium, 2. We get back to that full set of orbital. So just to remind you about electronegativity, as I mentioned, fluorine is the very, very top of the scale. It's set as 4. And you can see all these other very, very high electronegativity elements, nitrogen, oxygen, fluorine, chlorine, bromine. These are all the ones that we've talked about as gaining electrons over and over. Remembering these highest 3 electronegativity ions here will be helpful to you next year in AP or in AP Bio as well. But what we really want to think about is how different are their electronegativities. If I look at something which is definitely ionic, like sodium chloride, we can see there's a really big difference in their electronegativity. If I want to look at a compound which I know is covalent, like H2S, you notice hydrogen is 2.1, sulfur is 2.5. Those are only 0.4 away from each other. That's actually pretty close. So what atoms tend to form these covalent bonds? They are the ones that have to share electron pairs, and fundamentally it is the non-metals. Sometimes we can also think about this being applied to metalloids, but not consistently. So our always covalent kinds of things we look at: boron, carbon, nitrogen, oxygen, fluorine, sulfur, chlorine, bromine, phosphorus, selenium, iodine. Hydrogen will sometimes act as an ion, sometimes acts as a covalent. If hydrogen is with a non-metal, it often does act like a covalent bond because they're non-metals bonded together. So let's take a look at these options, and I'm going to let you pause this. You might go back and look at that table of electronegativities, or just think about metals and nonmetals. That's ionic. Two nonmetals together, that should be mostly covalent. So let you look at these and decide whether these bonds should be mostly covalent or mostly ionic. All right, well, carbon and hydrogen, two nonmetals. So that should be a covalent bond. Sodium is a metal, bromine is a nonmetal, metal and nonmetal says ionic. Manganese is one of our transition metals. Fluorine is a nonmetal, metal and nonmetal says ionic. Nitrogen is a nonmetal, hydrogen is a nonmetal, two nonmetals indicates that should be mostly covalent. Hydrogen and oxygen should be two nonmetals, mostly covalent. Rubidium and chlorine, metal and nonmetal, should be ionic. So think about what is in that bond, and also you can kind of think about where they are on the periodic table. The farther it is away they are on the periodic table, the more ionic that bond tends to be. We've talked about the diatomic elements before, but now we can see that these were all non-metals. They are all things that are going to form covalent molecular compounds with each other. And this is a reminder of this being, those 7 elements really need to be something that you know are diatomic. It's not written in on your periodic table. Make sure you write it in. If you don't have that Brinkelhoff mnemonic stuck in your head, or H. Broncliffe, I've heard that one too, make sure and put it in your head somewhere. We need to know that these are the ones that come naturally in pairs if they are by themselves. We have seen lots of compounds that have just one chlorine in it because it's an ionic compound and it forms just one, and you need just one chlorine to take one electron. These are only diatomic when they are by themselves. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I often call this the magic 7, is these 6 elements make the shape of a 7 to remind you to look for hydrogen, that 7th diatomic element. So that finishes up what we are doing right now with our molecular compounds. Those are non-metals bonded together by sharing a pair of electrons. And they use that different naming rules with a prefix so that you can tell how many of the elements are involved in the compound.